So today's seminar is focused on the supervised learning and classification of fire and traffic accident scenes. This work is addressing the theme area of promoting safety within the center, Mid-American Center, Transportation Center. So it's very important to address the safety of infrastructure and also operation of infrastructure and also the mobility. So I think this part of work is actually addressing the theme very well. Without further ado, I'm going to turn to the speaker, Professor Zhaozheng Yin. Professor Yin used to be at Rolla, Missouri, my colleague in computer science here at Missouri University of Science and Technology. He moved to Long Island, New York last year. So I think without further ado, I'm going to turn to Professor Yin. He has a current affiliation showing in the slides anyway.
All right. Thank you, Genda, for the introduction. And I really appreciate the funding support from MATS, Mid-American Transportation Center, for this exciting project. So collaborating with Dr. Qin and my student, MD, also we call him Pias, and we work out an interesting project on the fire and the traffic accident scene classification. Originally, the problem is from the hazmat transportation accident. And then later we thought we can generalize to more, such as fire or other traffic accident scene classification. So technology-wise, we will focus on the weakly supervised learning and also the spatial attention mechanism in the deep learning. So later we will introduce technical details. So today's roadmap is consisting of a few items. First, I will spend a few minutes to quickly overview the related deep learning background and also the spatial attention and the weakly supervised learning. And then we will discuss about the challenges and the motivations of this project. And then we will talk about our proposed architecture to attack these problems. So in our case, the classification can be both from the images from the camera, or it could be the video clips from the cameras. And later we will introduce the data sets we collected from the web, including the YouTube and the web search. And I appreciate actually UNL provides such a data portal for us to share this with the community. And then I will discuss about the results both in quantitative way and the qualitative way. And then followed is a conclusion. So we know in the past 10 years, actually, the hazmat transport incidents will bring a lot of unexpected damages. So the quick and effective response is critical to minimize the impact of the incident. So the first important thing will be we need to detect this transport incidents quickly, and then we can evaluate the severe level of this incident. Then we can have a quick plan to minimize the impact of the incidents. So that's our motivation for the safety thrust of the MATS. And our potential approach will be, we will use the signal from the camera. It can be the image or video. Video actually is a sequence of images. So the videos or images can be captured from the surveillance camera on the road, or it could be from the dashboard cameras, like mounted inside the car, right? And then the challenging problem will be, okay, if we want to solve this detection problem, we need to mine this visual information from the image. If this is video, video has temporal information. Therefore, we need to add the temporal information to solve this problem. And most of the current method, maybe the latest method, will be from the deep learning or neural networks based method. And importantly, most of this will be fully supervised method, right? And then we will see how we solve this problem in a weakly supervised way. So before we talk about the difference between weakly supervised and fully supervised, let me give you a few slides to review the basic concept of the deep learning and the artificial neural network and the spatial attention. So we know the deep learning actually is kind of complicated or deep neural networks. Try to learn the rich hierarchy representation, I mean the feature representation automatically. So here is one example for the image classification. For example, like we want to classify if this is a cat or not, right? And then sequentially the deep networks can extract the low-level feature, mid-level features, and high-level features. Low-level features can be the basic like a corner or edge, and the mid-level features can be from the region. And then high-level features may be from the overall objects or some parts of these objects. And then based on these high-level features, we can have some fully collected like a layer, which can be like performed as a classify. And then we can have the output. So classify which class of this image is, if this is a cat or if this is a dog, right? So this is the basic idea of the deep network. So originally, long time ago, when we talk about the artificial neural network, the structure is like this. We have the input layer and the many hidden layers, and then one output layer. Actually, the input layers can be the image, although image looks like a two-dimensional matrix, right, with the height and the width, but we can vectorize that image. Therefore, it will be like a vector here as the input layer. And then for the output layer, if we are doing the detection or classification, binary classification here, we want to see if this is an image with fire or without fire, then that's like a binary classification. So in our case, we add one more class such as the smoke. So that's a 3-class classification problem here. So the hidden layers actually can be corresponding to the different levels of the features. Right. So the third thing we want to mention will be the one type of the deep learning, such as CNN or convolutional neural networks, actually are quite successful for the image classification. So some of the basic operations, including the convolution, which actually is a feature extraction operator. It can select a feature and also filter out some useless informations, and they include some other operations such as the pooling or some nonlinear functions such as ReLU or rectified linear unit. So we must have some nonlinear function here. Otherwise, a sequence of the like a linear like a hidden layers will be equivalent to a linear function, right? So we have some nonlinear function following the convolution, right? So at the end, this is a fully collected layer, which perform just like a classify, right? And the fourth thing I want to mention will be for the video, because we have the time series signals, basically will be the image sequence. So in the past, such as conditional random field or hidden Markov chain actually is popular to explore the temporal information. So recently, the recurrent neural network actually try to solve this problem, especially like recently people solve this problem as a many-to-many like a way. So your input have many sequence of the image, and output can also have the like a sequential of the output. So to overcome some like some problem similar to the gradient vanishing shortcoming, and the long short-term memory LSTM actually is another particular type of the RNN which can work better in the practice. So in our case, we use this actually to explore the relation between the features among the sequence of the images. Right. So the last introduction will be what is the difference between the fully supervised and the weakly supervised. So for the fully supervised learning, for our detection, we will see usually the annotations, the human annotators will provide where is object. For example, if we're talking about the fire detection, then we want to know where is a fire. So usually we provide a bounding box in the image. So we know that there is a fire there. So this is the fully supervised learning. And in our definition for the weakly supervised learning, we do not have a definition of the box to tell us where is a fire. We just have a image level annotation, such as we just classify this is the image with fire, but we didn't tell the algorithm where is the fire. So the weakly supervised will save a lot of time of the human annotators who annotated the image, but it will be more challenging for the algorithm to solve this problem, right? So now let's take a look at the challenge and also the motivation of our project on the fire and the traffic accident scene classification, right? So for our transported incidents in the image, we know from different angles, the fire or accidents may not occupy the entire image. So here are a few examples, right? Therefore, we can imagine some of the pixels in the image are more important than the others, right? So the first challenge will be, so if we train a neural network, we are trying to extract the features, how can we pay more attention to the image regions which are directly related to the class, such as the fire or traffic incidents, and put less attention to the background or other unrelated image regions, because for our weakly supervised learning, we do not have the box to annotate the region related to the class we are interested, such as the fire or the traffic incidents, right? And then the second challenge will be the weakly supervised learning. We know most of the modern deep learning based object detection algorithm, so the mask, RSN, and other related algorithm actually are fully supervised. We use the bounding box, even the accurate segmentation mask for the training purpose. But in practice, if we have to do this in such a way, then we need to spend a lot of human effort to label the data. Collecting data actually is also tedious. And then if we want to label this, providing the mask or the bounding box is more time consuming, right? But if we think in another way, if we just trying to collect the data and give the image label, if this is a fire or a loud fire, then that is much easier rather than just providing the accurate box or segmentation mask. So our second challenge will be if we collect an image data set, which is only weakly labeled. Basically, each image has the image level label, but we do not have the accurate bounding box. So how can we effectively train a deep learning algorithm to fulfill this task? That's our goal. So to solve that problem, our pipeline of the algorithm will be like this. So given the input image, we're trying to extract the features. So we use CNN pre-trained in the image lab, which is a popular large-scale data set. And then we apply this input feature to the spatial attention model. We can learn actually the weights to calculate the important regions of the image. And then we use that as the input for our classification module, right? So here are some details about the architectures. So for the feature extraction, we use the VGG model 16 or VGG 19. We will show the results later, right? And then we extract the feature. So the feature actually is the domain of K1, K2, and F. K1, K2 is related to the image size, and F is related to the feature channels. So in this case, after the rescale, the K1 and K2 is, if I remember correctly, maybe it's about 11 by 11. It's small. F is like 512. We have a lot of channels of the features. And then we design a spatial attention module. So if we have the K1, K2, F, so this is a three-dimensional matrix. then we can vectorize this K1, K2 into K. Therefore, we can have the new two-dimensional matrix K by F. And then based on this input feature, we can learn actually one weights, right? So Y actually will be corresponding to the attention. And then this attention actually will be passed to a softmax function. Basically, it's normalize this one, and then the sum actually will be 1. So it's a normalization step. And then we apply this attention to the original feature vector, not feature vector, feature matrix, capital Y. Then we can have the attention for the feature vector, V. Now, based on this V, our classification module actually will be like a FC, fully collected network. So the parameter is W. And then after we apply this W to this attentionally for the feature vector, then we can get the output S. So S actually is a vector to predict if this is like which class this image is. So capital C means the number of class here. If this is fire, smoke, or no fire, then this C actually equal to 3, right? Okay, so first let's look at if we have the video recognition, how can we attack this problem? In the image, we just show like how do we actually extract the feature and design the spatial attention and then do the classification. Now for the video, we have the temporal information. As we mentioned in the introduction, we explore the long-short-term memory actually to explore the temporal information. So our structure is quite straightforward. Given the input video, this can be considered as a sequence of image. So for each image, we can extract the feature. And then for each feature, we again apply the spatial attention mechanism. But there is a difference here. So we apply the LSTM actually onto the spatial attentionally toward feature vectors into the LSTM. As I mentioned before, the LSTM can do the many-to-many. So here is the basic many-to-many. You have the many input and you have the many output. So for each image, you can have the classification module. And then overall, we average all this output from the classification module. Then we can have one label for the input video to classify if there is an accident or fire inside the image or not, right? So that's our overall architecture for the video-based recognition. Next, I want to introduce the data sets and the results. I think this could be valuable for the community, especially the data set. So the first data set we collected is about the fire data set. We collected actually 68,000, almost like 70,000 images from 3 classes. So we evenly distribute the images. So all like roughly 1/3 belong to the fire class. Another third belong to the elective class. Specifically, we collect another class is the smoke class. Basically, it's not obvious like a fire, but it's similar to the fire. And to like put more challenge into our like data set for the elective class, we also collect some images, which is quite similar to the like fire class, and but it's not actually fire. Even like some picture with a pizza, right? So we are trying to fool the data set, not fool the data set, fool the classifier to see how well it can perform, right? So that's the first data set for the image-based fire data set. And then the next data set we collected is traffic accident image data set. So at the beginning, we collect the traffic accident, we only use the image. And then later we collect the video. So for this image data set, we collect about like more than 1,000 image from 2 classes, accident class and the non-accident class. And then later we collect the video data set from the YouTube. So also we evenly distribute this. So maybe 1/2 is from the accident class, another is from the non-accident class. So here we can see some of the examples about the accident and the non-accident. And the second one here is a non-accident image video sample. All right. So here is a link actually from UNL, and if you are interested, you can download this data set, which consists of 3 parts. One is a fire data set image, and the other one is a traffic accident image related, and the third one is a traffic accident on the video based. Right. And now let me show you some of the results. I think the results were almost like 1 year or 2 years old. The paper was published last year. All right. And for the quantitative evaluation, first we show what is the fire classification accuracy. So we compare our method. Our method is the last column. We compare our method with 2 like classical methods. The first one is a support vector machine, which is a kernel method. And the second one is just like a neural network without the attention module. And in this case, we use the VGG16, which is one type of the CNN models. And we tried this 4 times. Basically, we randomly split the data set. Like one portion of them belong to the testing. The rest actually belong to the training. And then we want to see the performance, right? And then we compute what is the average of the 4 trials. So our results actually outperform the network without the attention module. And then the second experiment that we performed is we tried a different like a CNN model to see if this is heavily relied on the baseline or not, right? And then we found out the VGG16 is slightly better actually. This is just we do a little bit like a detailed analysis. So we want to see what is the accuracy over each class. So we can say actually the VGG16 is better actually for the smoke class, and the fire actually is almost the same. And for the negative is almost the same, but on average, VGG19 outperform VGG16 a little bit. Therefore, in the rest of the experiment, we use the VGG19 as the feature extraction. All right, so the third one I want to show you will be what is the performance of this algorithm on the traffic accident scene classification. Use the image. Again, we tried like 4 times and compute the average. So the baseline is VGG19 classification without the attention pipeline. And we got about 88 or 89 like percent accuracy. And then use the spatial attention model, we boosted the performance by 4 percentage points. The last one is traffic accident scene classification based on the video. Okay, so for this video, we also compare this with like a few like operation study. The first one is a baseline approach, the image based. And then the second one is we apply the spatial attention model. And then the last one is ours. Based on the spatial attention model, we have the LSTM model, LSTM. And then we can see LSTM actually boosted the performance by more than 2 percentage points. Right. Now I want to show you some of the qualitative results. So here is the example on the fire detection on the image. We want to know if our spatial attention mechanism can really focus on the important image regions. So here we use a heat map to show where are the important image regions that are related to the fire detection. So for those cases, as you see clearly, so those heat map actually emphasize important regions. So here I want to show you a few more examples. Now the second qualitative evaluation is for the traffic accident image classification based on the images. So just for the like image based, and I mean single image based, we want to show what is the like attention model. Like for this one, there is a small sedan actually had an accident with this with this truck, and then the attention actually paid like clearly on these regions, and a few more examples here. All right. So since this actually are videos, then I can show you like how this attention is generated over time on the like a video. So the left one is the original video, and the right one is a video with spatial attention. We want to see like which regions inside the video contain the information related to the traffic accidents. So this one looks fine, and I want to show you one not so good case. All right. So as you see from this case, original video left, and this is the right. So we can see most of the time, especially during the accident, then we can focus on these regions where the accident happened. But in the meantime, we also see there's some flickering observation inside the video. So this thing actually is more complicated. And there's some future work we can consider. For example, our current attention is only paid on the image. So it's image-wise. We didn't consider the attention over the time, right? So that's one thing we need to consider to improve the current performance. Right. So in summary, we introduced a framework for the fire and accident scene classification. So some of the challenges we're interested in will be, we want to know inside the image or video, which regions are more important for the classification task, because this is related to the weekly supervised learning. When we do the classification or detection, we do not know where is the traffic accident in the image, where is the fire in the image. We just have the weak label, the image level label, right? The second contribution we want to mention will be, we build a data set consisting of 3 subsets: the fire, the traffic accidents of images and the videos, and share with this community. And hopefully this can boost the development in the hazmat transport accident detection. So that's my short presentation. And here is the reference and the link for the dataset. And again, I want to thank Mass and Genda for the support in the past years. Thank you. And any questions?
Thank you very much. Now open up for questions. You can ask, speak up directly, or you can also send in chat. Maybe I can start with a question.
Sure.
First, when you look into the temporal information, you take image frame from a video file evenly, or the delta T is evenly or manually picked at different time instead?
Yeah, that's a good question. If the video is very long, so if we do this frame by frame, it may not be efficient. But right now for us, this is a very prototype experiment. Therefore, the video clip is quite short. Therefore, we extract this frame, a lot of frames evenly. Mm-hmm. So that's something we are currently doing. For the attention, we can pay attention to the specific image. But for long video, such as the video, if this is 1 hour or 24 hours long, how can we pay attention to the related video segments or video clips? So that's the temporal attention in the video. Mm-hmm.
Right. So I suppose if you use more frames, you can also reinforce the attention model to make it more accurate, because you have a temporal correlation, right?
Right. If we can find out more important frames, therefore we won't do this average, right? So we know which frames are more important.
Any other questions from audience?
I don't have any questions on chat.
Yeah, I didn't see any on chat.
No question, just a comment. I think this is really interesting work, and it's really important work to look at continue to look at ways to better model events of this kind. So I applaud you and your co-author on a great job.
Thank you.
I just have one question.
Yeah,
Yes,
go ahead.
please.
All right. I didn't hear much about the existing kind of system that you have. I know you talked about evaluating the others compared to yours, and the differences in the evaluation I foresee wasn't too much a gap, even though it was an improvement. Is there any other aspect of your system that is more different than existing systems?
I don't know if I understand your question like fully. You mean like another application, or in the evaluation we want to do more experiments? Can you rephrase your questions?
All right, let me come again. In your evaluation slide, you compared your system with others, right?
Yes.
Okay. I just wanted to know, I've seen that the differences between yours, even though yours was kind of an improvement, but it wasn't that much of an improvement. I want to find out, is there any other aspect that the other systems are kind of lacking that yours is able to kind of fit into that lack or the gap that is in the other system?
Yeah, I think that's a you know, if we propose a task, new problem, and we collected 3 data sets, and then our performance is close to 100%. That means we just open the door and then we close the door for the community. I want to say what we collected this data set, and then we showed that such a, I will say this is kind of promising. Right now we have the 86% accuracy, and this is over like 60,000 images. And if someone else is interested, then they can try to improve based on our current one. So there is still room to improve that. There is still 14 percentage points to approach the 100%.
I think
All right.
he's trying to ask is, if I may rephrase that, is do you see any significant different consideration in your model versus their model that results in this difference? I think that's what he's trying to.
Yeah, for this one, like I want to say, especially for this one, we're trying to say if we apply the spatial attention, the model actually improved by roughly like 3 percentage points. So maybe you will say the 3 percentage points is not a big gap, but you know, like when you want to bump the like performance, like from the 80 to 85 to 90 to 95, or like 100. So it's not easy, but if you want to improve the performance from 60 to 80, then maybe that's a little bit easier. So here we want to show you like the spatial attention mechanism did help to improve the performance from a basic neural network to like a spatial attention enforced neural network. Yeah, I don't know if I answered the question correctly.
Yeah, you did. Thank you.
Any others? Well, if not, then maybe let's seminar. Thank you, Dr. Yin, for your interesting presentation, and we hope you participate in future maths seminars that will be announced through the network. Thank you very much.
All right, thank you all for the attention.